Chapter 4, Probability. This lecture is on Section 4-1, Basic Concepts of Probability. The single most important objective of this section is how to interpret probability values, which are always numbers between 0 and 1. So a small number, such as 0.001, corresponds to a rare event. A number such as 0.998 would be a very likely event. And we'll also talk about odds, which are come up more often in lottery and gambling applications. So some of our basic terminology here: an event is any collection of results or outcomes of a procedure. And a simple event is an outcome that cannot be broken down further into simpler components. And the sample space of a procedure or experiment consists of all possible simple events. So the sample space consists of all the outcomes that cannot be broken down any further. We have an example here. A single birth could be an example of a single birth could be one girl baby. The sample space of a single birth would be one boy baby or one girl baby. Suppose you were to have 3 consecutive births. Then one example of the event of 3 births occurring would be 2 boys and 1 girl. And that could happen in several different ways. You could have a boy, and then a girl, or a boy, then a girl, then a boy, or the girl first, and then a boy and a boy baby. So the sample space would have to include all the possibilities: 3 boy babies, 3 girl babies, 2 boy babies and 1 girl baby, or 2 girl babies and 1 boy baby, and their various permutations. It's no coincidence that 3 births, 2 possibilities, boy or girl, results in 2 to the 3 outcomes. And note, we have 8 simple events in our sample space for a procedure of 3 births. With 1 birth, the result of 1 girl is a simple event, and the result of 1 boy is another simple event. They are individual simple events because they cannot be broken down any further. With 3 births, the result of 2 girls followed by a boy is a simple event. When rolling a single die, the outcome of 5 is a simple event, but the outcome of an even number or an odd number is not a simple event. Because getting an even number can be realized by rolling either 2, 4, or 6. However, the outcome of rolling a 5 is only realized when you roll 5. something that's not a simple event. With 3 births, the event of 2 girls and 1 boy is not a simple event because it can be realized in these several different ways here. An example of a simple event would be the first baby girl, second baby boy, and third baby a girl. Sample space. So with 3 births, the sample space consists of 8 different simple events. This 8 here is 2 to the 3rd. A single birth well, let's consider this example. With 2 births, an example of such event would be 1 girl and then 1 boy. So list out the simple events that comprise the sample space for such a procedure. Go ahead and pause the video and give it a try. Alright, so you could have 2 boy babies, a boy baby and then a girl baby, a girl and then a boy, or 2 girls. And note the size here is 2 to the 2. 2 events. Each event has 2 possibilities. 4. Describe the sample space for tossing a fair coin 4 times in a row. So what is the probability of getting 2 heads and 2 tails in any order? Well, let's start off with getting 4 heads in a row. Right? And then we could get 3 heads and a tail. And then let's move the tail through the various positions here to get all the possibilities with 3 heads and 1 tail. So 2 heads, a tail, and heads. 1 head, tail, 2 heads, tails, and then 3 heads. And that exhausts the possibilities of 3 heads and 1 tail. Now let's consider 2 heads and 2 tails. So we need to permute. That means take these 4 elements here and find all their different the ways of arranging them together. So we could move this block of 2 T's into the middle. So H, T, T, H. We could move them all the way to the left. So T, T, H, H. And we could think of just moving this T over. So H, T, H, T. And then move this one over. T, H, H, T. And what else could we do? We could do H, T. No, already did that one. You could do T, H, T, H, which sort of matches up with that. Just as this permutation and this permutation match up together. And yeah, that exhausts the possibilities for 2 tails and 2 heads. So then we could have 3 tails and a head, and then we move the H through. 2 tails, a head, and tails. 1 tail, 1 head, 2 tails. Heads, tails, tails, tails. And then finally, all tails. We'll learn more about counting up sample spaces in future sections, but we have 4 events, and each time it could be either heads or tails, so that's 2 outcomes, 4 events, 2 to the 4th, 16. Let's count up our sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Good. So what is the probability of getting 2 heads and 2 tails? Well, the probability of getting 2 heads and, let me write out and 2 tails would be, alright, count up this row here. So the simple events with 2 heads and 2 tails consist of 6 simple events. So take the number of simple events from the sample space that satisfies the condition, and then we have the size of the sample space, divide by the size of the sample space. So that's exactly 0.375. So it's less likely, it's more likely that you'll get some other combination, but it's not necessarily rare. Alright, so go ahead and pause the slide and fill in these blanks here, and note 16 possibilities. Okay, very good. Here you would have a tails and then 3 heads. And let's see, here we would have tails, heads, heads, tails. And then here we would have 3 tails and a head, and then tails, 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 tails. Some notation for probability. So we use P to denote probability, and capital letters for specific events. So then we would say P of A means the probability of event A occurring. Alright, so numbers, a probability of 1 means definitely going to happen. The closer the number is to 1 is the more likely it is. Probability of 0.5 means it's a 50-50 chance. And a probability close to 0 is unlikely, and it's not going to happen if it's 0. So probability of any event will be some number between 0 and 1. Possibly 0, possibly 1. Here's our definition for the relative frequency approximation, the one we used up in the example above. So you take the number of times that an event occurs and divide it by the number of times the procedure repeated. So this would be more for an experimental, if you were conducting some experiment to see, to conclude the probability of an event. For instance, if you were to flip a coin 10,000 times and then record that it was heads 5,000 and 50 times, and then it was tails 4,950 times, that would be a reason to conclude that flipping a coin was about a 50-50 chance. The classical approach assumes that all outcomes are equally likely. We can't always use this in real-world approaches. We'll see an example here soon. But what you do is you take the number of ways that A occurs and divide it by the number of different simple events. And subjective probabilities are estimated by using knowledge of the relevant circumstances and common sense. And simulation can be used to get an idea of the probability of a certain event occurring. And this is becoming more common nowadays as computing power is increasing. So we will either leave our probabilities as exact fractions or round to 3 significant digits. Since they're numbers between 1 and 0, we would expect 1.0 for the case of 1, 0.0, and then 0, and then several digits over here. But we won't count the 0, so we'll need 3 digits here. The law of large numbers is that procedures repeated again and again, the relative frequency probability of an event tends to approach the actual probability. Some things we need to look out for, though, are that the law of large numbers applies to behavior over a large number of trials, and it certainly does not apply to any one individual outcome. And if we don't know anything about the likelihood of different possible outcomes, we should not assume that they are equally likely. So we'll look at this example, the probability of dying when making a skydiving jump. Okay, so the probability of a skydiving death will equal the number of skydiving deaths over the number of skydiving jumps. So the total number of skydiving jumps here was 3 million. And the total number of skydiving deaths was 21. So using this frequentist approach, this would reduce to 7 over 1 million. Which would be 0.12345 So 0.000007. Very close to 0, so very unlikely to die from skydiving. And this is an example where the classical approach cannot be used because the outcomes of dying and surviving are not equally likely at all. Let's take an example of texting and driving. So it was found that 3,785 high schoolers were texting within the last 30 days while driving, and 4,720 did not text. Okay, so we'll use this hash symbol for size, the size of the sample, or we'll just say sample size right now, is equal to, well, the teens that texted plus the teens that did not text while driving within the last 30 days. So let's see, that would be 5, 0, 5, 8,505 total. So find the probability that a given student or high school student texted while driving the last 30 days. So probability, we'll just say texted, would be those who texted, the 3,785, divided by 8,505. And we'll see that that reduces to 0.445. Complementary events. This is the key idea. So the complement of an event, denoted by A with a bar over it, a complement, is all the outcomes in which the event A does not occur. So you need to get used to thinking of what is the opposite of some event, the exact logical opposite. So the opposite of dying would be surviving. So the probability of not dying would be the probability of the complement of dying. So it's always going to be 1 minus the probability of whatever event you're talking about. So the probability of not dying, the opposite of dying, is 1 minus the probability of dying, which is 1 minus 0.000007, which would be 0.999993. So very likely to survive. In general, the probability of a complement is 1 minus the probability of A. And notice that if 21 deaths occurred out of 3 million jumps, then that means 2,999,979 jumps were survivors. So you would take that number of surviving jumps divided by the total number, and you would get this same number we just computed, 1 minus the probability of not dying. the rare event rule for inferential statistics. So if under a given assumption the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude the assumption is probably not correct. So significantly high number of successes, X successes among N trials is significantly high if the probability of X or more successes is unlikely with a probability of 0.05 or less. And this 0.05, some research groups might want to go with 0.02 or 0.01 or something less. That's a judgment call. And likewise, that is for a significantly low number of successes, the probability of X or fewer is less than 0.05. Okay, so here's a review of what we've learned. Probabilities have to be numbers between 0 and 1 inclusive. Probability of 0 is impossible. Probability of 1 means absolutely certain to occur. Here's our notation for the probability of an event. Here's our notation for the probability of the opposite of a given event, or the complement. Odds. This is more in sports and in gambling, so we won't spend too much time on this. But we define the actual odds against an event to be the probability of the complement divided by the probability of the actual event. So a ratio here is really another way of expressing a fraction. So 16 to 4 is equal to 16 over 4. Then odds in favor, well, odds in favor would be to take the probability of the event divided by the probability of its complement. So the payoff odds against event A, so when it's against, you do the complement over the probability of the event. And then here we have another ratio, so that's net profit divided by amount bet. So let's consider the following example. If you bet $5 on the number 13 in roulette, your probability of winning is 1 out of 38. The payoff odds from the casino are 35 to 1. So find the actual odds against the outcome of 13. Right? So the actual odds against the outcome would be the probability of not winning divided by the probability of winning. So your probability of winning is 1 over 38. The complement probability of not winning would be 1 minus probability of winning, or 1 minus 1 over 38, which is, you could turn this 1 into 38 over 38 minus 1 over 38, so 37 over 38. Put that here. And then that's equal to 37 over 38. When you have fraction divided by fraction, take the reciprocal of the bottom fraction and multiply it to the top. So 38 over 1, the 38's cancel, and we have 37 over 1. Or 37 to 1 in gambling parlance. So how much net profit would you make if you win by betting $5 on 13? So that's the amount bet, right? And remember, we had payoff odds against is equal to net profit over amount bet. So our payoff odds against were 37 to 1. Net profit is what we would like to know. And the amount bet was $5. So we can solve for net profit by multiplying $5 to both sides. And then what's that? 150 plus 35. 185. I'm using the casino uses payoff odds of 35 to 1, so I'm actually answering the next question. This should be 5. So payoff odds against casino. So the casino is not going to use the actual payoff odds against. It's going to take a small cut even if you win. So it uses less favorable odds. So 35 here over 1 would be the casino payoff odds. So in that case, it would be 5 times 35, 175 here. And that's the net profit. You also get your $5 back, so 180 total. Now, if the casino were not operating for profit and used the actual payoff odds against that we calculated earlier, then you would have 37 over 1 equals net profit over amount bet, which would be $5. And similarly, using the same algebra as before, we would get $185. And that concludes this lecture.